The James Webb Space Telescope, JWST, habitually hailed as the substitute for the Hubble Space Telescope, has changed how we decipher the universe. Since its launch, the telescope has provided a surprising perspective on the universe, uncovering secrets and revealing regions previously unimaginable by humanity. The JWST's state-of-the-art technology has allowed scientists to look into the farthest reaches of space, examining galaxies, stars, and planetary systems formed billions of years ago. This article delves into the various aspects of the JWST, from its engineering marvels to its landmark discoveries, and examines how it has reshaped our understanding of the universe. To appreciate the significance of the JWST, it is essential to understand its predecessor, the Hubble Space Telescope, launched in 1990. Hubble provided astronomers with the first clear images of distant worlds, nebulae, and stars, free from the obscuring effects of Earth's atmosphere. Hubble's contributions to science are immense, from determining the rate of the universe's expansion to observing the impact of comet Shoemaker-Levy 9 with Jupiter. Its deep field images, capturing light from galaxies billions of light-years away, have given us a glimpse into the early universe. However, despite its successes, Hubble had limitations. Its primary mirror, with a 2.4-meter width, restricted its light-gathering ability, and its instruments were designed for ultraviolet, visible, and near-infrared parts of the spectrum. As astronomers pushed the boundaries of our understanding, it became clear that another telescope was needed, one capable of observing in the infrared range, where it could peer through cosmic dust clouds and observe the universe's earliest galaxies. The concept for the James Webb Space Telescope began to take shape in the 1990s, even before Hubble had reached its full potential. Named after James E. Webb, NASA's administrator during the Apollo era, the JWST was envisioned as the next great observatory, a telescope that would look further back in time than Hubble, capturing light from the first stars and galaxies that formed after the Big Bang. The JWST design presented significant engineering challenges. Unlike Hubble, which orbits Earth at an altitude of around 570 kilometers, the JWST would be positioned at the second Lagrange point, L2, approximately 1.5 million kilometers from Earth. This location provides a stable environment with minimal interference from Earth's heat and light, but it also means the telescope cannot be upgraded or repaired by astronauts. To observe faint distant objects, the JWST required a much larger mirror than Hubble's. The solution was a segmented mirror made of 18 hexagonal, gold-coated segments, providing the telescope with a total diameter of 6.5 m. This mirror had to be folded to fit inside the Ariane 5 rocket and only deployed once the telescope reached its destination. The JWST also required a sun shield to block heat and light from the sun, Earth, and Moon, keeping the telescope's instruments at a temperature just a few degrees above absolute zero. The sun shield, the size of a tennis court, is made of 5 layers of a special material called captain, which can withstand extreme temperatures. After years of planning, delays, and cost overruns, the JWST was finally launched on December 25, 2021. The launch was a pivotal event watched by scientists and space enthusiasts worldwide. The Ariane 5 rocket delivered the telescope into space, and over the next 30 days, the JWST embarked on a complex, meticulously planned sequence of activities. The telescope's sun shield was the first major component to deploy, a process that involved various systems and thousands of parts working in unison. Any failure at this stage could have jeopardized the mission. Once the sun shield was successfully deployed, the mirror segments began to unfurl and adjust themselves. This process took several weeks, as each segment had to be positioned with nanometer precision. By mid-2022, the JWST had completed its commissioning and calibration, and its instruments were ready to start collecting data. The first images released to the public were stunning. The telescope's ability to see in the infrared revealed the universe in a new light, with breathtaking clarity and detail. One of the primary goals of the JWST is to observe the first galaxies that formed after the Big Bang billions of years ago. These galaxies are so distant that their light has been stretched into the infrared range due to the expansion of the universe, a phenomenon known as redshift. Hubble could detect these distant objects, but the JWST's infrared capabilities allowed it to observe them in detail. In its first year of operation, the JWST made several historic discoveries. One of the most significant was the identification of galaxies that existed a few 100 million years after the Big Bang. These galaxies appeared larger and more evolved than previously thought, challenging existing theories of galaxy formation and evolution. Researchers had long believed that the first galaxies were small and gradually grew over time by merging with other galaxies. However, the JWST observations suggest that some galaxies formed much more quickly and grew larger sooner than expected. This finding has prompted cosmologists to reevaluate their models of galaxy formation and evolution. The JWST also captured images of enormous structures that had never been seen before. For instance, the telescope observed the intricate details of the cosmic web, a vast network of filaments that connects galaxies across the universe. These filaments, made of dark matter and gas, act as the scaffolding on which galaxies form and evolve. The JWST's observations of the cosmic web have provided new insights into the large-scale structure of the universe and the role of dark matter in shaping it. The JWST has also transformed our understanding of star formation and stellar evolution. Stars form in dense clouds of gas and dust, which block visible light. However, infrared light can penetrate these clouds, allowing the JWST to observe the process of star formation in unprecedented detail. One of the telescope's first targets was the Orion Nebula, a stellar nursery located about 1,344 light-years from Earth. The JWST images revealed numerous young stars, some still embedded in their birth clouds. These observations have provided new insights into how stars form and evolve, as well as the processes that lead to the formation of planetary systems. The JWST has also observed the final stages of stellar evolution, capturing stunning images of dying stars and the clouds they create. These observations have shed light on the processes that govern the end of a star's life, including the formation of white dwarfs, neutron stars, and black holes. One of the most intriguing aspects of the JWST mission is its ability to study exoplanets, planets that orbit stars outside our solar system. The telescope's instruments can analyze the atmospheres of these distant worlds, searching for signs of habitability and potentially even life. In its first year of operation, the JWST made several key discoveries related to exoplanets. One of the most notable was the detection of LHS 475b, an exoplanet located about 41 light-years from Earth. This planet is roughly the same size as Earth and orbits its star in just 2 days. The JWST observations revealed that LHS 475b has a thick atmosphere, potentially composed of water vapor, carbon dioxide, or methane. The JWST has also observed other exoplanets with a range of atmospheric conditions. Some of these planets have thick, cloudy atmospheres rich in methane and other hydrocarbons, while others have clear atmospheres dominated by hydrogen and helium. These observations have provided valuable information about the diversity of planetary systems and the conditions that could support life. Perhaps one of the most compelling questions in cosmology is whether life exists elsewhere in the universe. While the JWST cannot directly detect life, it can search for biosignatures, chemical markers that may indicate the presence of life. For instance, the detection of oxygen or methane in an exoplanet's atmosphere could suggest the presence of biological processes. The JWST's ability to study exoplanets has opened a new era in the search for life beyond Earth. As the telescope continues to observe more planets, it will provide crucial data that could help answer the age-old question, are we alone in the universe? In addition to its studies of distant galaxies and exoplanets, the JWST has captured images of some of the most beautiful and bizarre objects known to humanity. One of the most striking is the Tarantula Nebula, a massive star-forming region located in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. The Tarantula, also known as 30 Doradus, is a vast region of gas and dust where thousands of new stars are being born. The JWST images of this area reveal intricate filaments of gas, glowing clusters of young stars, and the remnants of supernova explosions. These observations have provided new insights into the processes that drive star formation and the life cycles of massive stars. The JWST has also captured stunning images of nebulae, such as the Eagle Nebula and the Pillars of Creation, revealing details that were previously hidden from view. These images have captivated the public's imagination and provided valuable data for astronomers studying the birth and death of stars. While the JWST has made incredible strides in our understanding of the universe, its journey has not been without challenges and controversy. The telescope's development was plagued by delays and cost overruns, with the final price tag reaching nearly $10 billion, far higher than the initial estimate. These issues sparked debates among scientists and policymakers about the feasibility and worth of the project. Some critics argued that the resources allocated to the JWST could have been better spent on other scientific endeavors, while others contended that the telescope's discoveries would ultimately justify its cost despite the challenges. The JWST has already demonstrated its immense value. Its discoveries are reshaping our understanding of fundamental questions about the universe, such as the formation of galaxies, the life cycles of stars, and the potential for life on distant planets. The unprecedented data it collects will fuel scientific research for decades, paving the way for future missions and advancements in astrophysics. In the broader context of space exploration, the JWST also serves as a testament to human ingenuity and collaboration. Built by an international team of scientists and engineers, the telescope embodies a collective effort to push the boundaries of knowledge. Its success will inspire future generations to explore the cosmos and answer the profound questions that remain about our existence and the nature of the universe. As the JWST continues its mission, astronomers are eagerly anticipating the wealth of data it will produce. Each new observation promises to unveil more about the history of the universe, the formation of stars and galaxies, and the intricate dynamics of cosmic structures. With its capabilities, the JWST is not just a tool for discovery but a gateway to understanding our place in the cosmos. In summary, the James Webb Space Telescope stands as a revolutionary instrument in the field of astronomy. It is not merely a successor to Hubble, it represents a new era in our quest to unravel the mysteries of the universe. With each image and each data point, the JWST deepens our appreciation for the cosmos and reaffirms the idea that we are just beginning to scratch the surface of what lies beyond our planet. As it reveals the universe's hidden wonders, the JWST invites humanity to dream bigger and explore further than ever before.